and good evening. I would like to thank you all for coming to our next installment of the MoCA Public Talk seminar series. So last semester we had 4 brilliant talks, and we get to continue that with Daniel Price tonight. So Daniel is one of our own. He's been at Monash for several years now as an ARC fellow. He also got his beginnings here doing his honors thesis at Monash. Then he left for a while, spending some time at Cambridge and in Exeter, and now he's back and doing great research with the department, helping out in a lot of the public events such as this. And now he will be giving the public talk on Is There Life Out There? So without further ado, I'll pass it off to Dr. Daniel Price.
Thanks, James, for the warm introduction. Is my microphone on? Can you hear me? Good. There's some familiar faces. See from the ASV. Hopefully you haven't heard this talk before. I decided I'd be a bit more speculative tonight. And it's a bit I thought it was quite well timed with some recent announcements. So let's get to the punchline. Have we found any aliens yet? That's what you all want to know. And I picked this question actually because I was in the kids' school and we asked the students in the class, what's the question you most want to know? And the question was, is there aliens? And really science is just like being big kids sometimes. So it might take us a little bit longer, but really it's the question we're all interested in is there aliens? Now, all right, I'll try this one first. So this kind of might be the sort of thing we're looking for. This is one done by a famous artist who is in the room. So I can tell you right now that we haven't seen anything like that. So this is the artist's impression. And every time we don't resolve something properly, you have to put up with the artist's impression. So let's keep that impression in your mind while we go through some of what we do know about aliens in the universe. Or the possibility of alien life, perhaps let's put it that way. And I want to talk a little bit towards the end about this particular picture because for me, in the field that I work in, which is how stars and planets are born, it's a particularly special image because it tells us it's a brand new kind of observation that we have of planets caught in the act of being born. All right, so the question is, are we alone in the universe? Where might we start looking? And I want to get some audience responses tonight, otherwise I have to tell jokes. And for the kids in the audience, every time you get a bit bored, if you put up your hand, I'll tell another joke. Go ahead. Right, so we might look for Mars, and why Mars has held such a kind of special place in our imagination. Well, first of all, most of you think of aliens like this, which is kind of your prototypical Martian. That's what we thought about the things living on Mars. Now, where did this come from? It came from the very first time we started to get telescopes and looked at Mars. So one of the very first maps of Mars was several hundred years ago by Giovanni Schiaparelli. That's the map you drew on the top left there. And a bit later, Percival Lowell came along, looked at Mars through a telescope and saw these kind of lines on Mars and put 2 and 2 together and made 5 and said, well, in fact, it was a slight mistranslation, but Giovanni Schiaparelli called them canali. And so Percival Lowell drew these as sort of quite straight lines and said, well, there must be a sign of an alien civilization living on Mars, and they're canals. All right, so what are these things? Is that really what they look like? And so that's what we had in our imaginations, a civilization of canal-digging aliens there on Mars, possibly green with little eyes on top. What does Mars actually look like? Does it look like that? Right, so it's pretty barren. And although I think there's a little bit of a twist to this tale because if you then go and look at what we now know Mars looks like from satellites in orbit around Mars, then what Lowell originally drew as these lines, you can see them as these giant kind of canyons on Mars. So the most famous one is this big sort of rip right across the surface. It's a huge canyon, like 10 kilometres deep on Mars, cut into the surface of Mars. It's pretty fantastic. Now, is there water in it? As of last week, no. So the interesting thing is, from last week, now, if anyone can tell me the name, there's an extra prize here. Prize is one less joke. So that's the name of the crater, but the name of the things which are now known to signify water on Mars have a special name. Brine, yeah, is kind of what these things are.
Dark patches.
Dark patches, they are. Does anyone know this? Very, yeah. So they've actually been talked about for a couple of years. So the thing that's been announced in the last few days is not a particularly new thing. It's just a sort of extra confirmation that it really is briny flows on Mars. But they're detected basically all throughout the canyon, especially deep in the canyon. They're called RSLs. Does anyone know what RSL stands for? It's completely scientific jargon. It's like sometimes when scientists want to talk about time travel, but time travel is like bonkers. So you don't want to publish anything. You don't want to write time travel in a scientific article. You want to write... So the way time travel is described is as a closed time-like curve. So if you want to write about time, I'm sure Kip Thorne will tell you a bit more about closed time-like curves in our next public lecture. But if you want to talk about water on Mars, you talk about RSLs, which are these recurring slope lineae, which is a scientific term for this sort of streaky stuff that appears inside the craters on Mars. And the interesting thing about it is sort of captured in this movie, is that now the new thing about Mars is we've actually been staring at it repeatedly with these orbiting satellites, so we can see things changing on Mars. So previously you just get, the odd picture. So you get these very high resolution images, and you can see in this particular crater up the top there, that you get these sort of streaky lines that follow the sun. So when the sun shines on a particular bit of the crater, you get these sort of streaks develop on the side of the crater. And that's what these recurring slope lineae, like straight sort of streaky things. And so they are the sign of these briny, what we now know to be salty flows on Mars. Now, is there anything living in them? Probably not. But it's kind of interesting that we've gone from, these sort of canal things being filled with water on Mars to actually there is some kind of water in those canals at least. Maybe not quite, little green things with boats and stuff, but it's better than we might have hoped for, at least in a pretty otherwise dry environment. All right, so that's Mars in a nutshell. Where else can we go to look for life? All right, so we've jumped, let's go further out in the solar system. Please tell me what this one is. Jupiter, very good. If you put up your hand, I have to tell a joke. So what did the jigsaw puzzle alien say when he landed on Earth? I come in pieces. So one of Jupiter's moons is Europa. So what's special about Europa? And you've seen in the background here from a picture New Horizons took several years ago on the way to Pluto. But Europa is special because it's covered in ice. Right, so the speculation is that maybe on Europa there's a sort of deep ocean underneath. It'd be very dark if there was there. But we know from Earth that things living on the bottom of the ocean, where it's very dark, definitely things can live there. So in particular, like a real surprise in the last 20 years is these black smokers discovered in the middle of the ocean floor that have absolutely no sunlight whatsoever. But they have whole ecosystems. And I'll give you, well, can you tell which one's the artist's impression here? But you can even see these little white things are like little shrimps living on the black smokers. So what's interesting about that is it's a sort of life which is not dependent on the sun, at least not directly. It's indirectly dependent on the sun. But for somewhere like Europa, where you don't have a lot of light getting down to the bottom of the ocean there, it's kind of interesting that we do have life on Earth that could potentially live in those kind of places. Now, well, there's a big unknown in all this, which is not my field, which is, well, how does life start? How did it start on Earth? And even if it wasn't my field, the people who are in that field don't know either. So they're not really going to be able to help you all that much. All right, so there's one more place in the solar system that's interesting in the search for life. Io is interesting, but it's pretty volcanic, and I wouldn't like to try and live there. But there's one more that's not too far away from Io. And it has... All right, so let's... Enceladus might also be interesting. Let's put my definition, not just there's at least one particularly interesting place where life might be. And there's a picture over there taken with Voyager. So Titan is a moon of Saturn. And in terms of a place that has things like Earth, can anyone tell me what Titan has that we now know of in the last 10 years? Methane lakes. Well, so first of all, it has a very thick atmosphere, so it's it has weather and clouds, and it rains, liquid hydrocarbons. So this is a picture taken, so you can't see much with telescopes of Titan because it has such thick clouds. But so Cassini mission took radar images, and so this is kind of a radar image of the surface of Titan. And if you think about when we first looked at the moon, you saw these dark patches, and they were called maria, like seas. On Titan, that's what these things really are. And in particular, the special thing that Cassini mission did was took a little hitchhiker with it. Does anyone remember the name? So the probe was called the Huygens probe, and we actually landed on Titan. And so here's what it's like to land on Titan. Here's a movie taken by the Huygens probe as it landed through the atmosphere. And the sound effects do mean something, but there's the parachute opening. And there's the pictures are the pictures that the Huygens probe took as it landed through Titan's kind of thick clouds. And I have no idea what the sounds are, but they're related to the pictures in some way. Now I'm going to speed it up in the middle because it takes quite a long time to descend. I'm going fast forward. So there's a lot of descent through quite thick clouds. And so it goes on. You start to see a bit of the surface. It keeps going, we'll speed it up a bit. We've got some pretty good snapshots of Titan on the way down. And, well, let's see the last bit. Going down. Still going down. Right, you better brace yourselves. Adopt the brace position. And helmets on. So we got the first pictures of something landing on the surface of Titan. And the interesting thing about the landing, that particular sound at the end, is it landed with a bit of a spludge. So it was a bit of a wet landing. And some of the best pictures of Titan are pictures that Huygens took on the way down. Now look at the picture on the left and tell me what that looks like. It looks exactly like a coastline with rivers. Now, for the kids up the back, there's extra bonus points, like I'll tell another joke, or maybe I won't tell another joke. That's the bonus point. But tell me what those rivers are made of. Go on. Methane. Now, do you know what methane is otherwise known as? Do you know where methane comes from on Earth? Go on. It comes from cows, and from you. Do you know where on cows it comes from? Comes from the backside of cows. So methane is really fart gas. And so Titan has like whole lakes and rivers of fart gas. So we think it'd be a lovely place to go for a boat ride is down the rivers of methane on Titan. And so there are plans afoot, and hopefully within our lifetimes we'll go back there. And there are plans to send some kind of boat to go and land in the lakes on Titan and maybe go for a little bit of a sail on the lakes of fart gas. But this is, I mean, this is a particularly interesting place. So it's obviously like a completely strange world and nothing like the Earth. But something rich in hydrocarbons, maybe you could support some kind of life completely different to life as we know it. But there's certainly this sort of raw ingredients there for something to be living on Titan. And it's pretty fascinating that such an alien world can look so familiar on the way down. All right, so there's the lakes that you would not want to go swimming in. Okay, so I sort of wanted to take the picture a bit bigger tonight, from things we can actually go to what we know about life on a much grander scale in the Milky Way. So the sort of 8 or 9, sorry Pluto, planets in the solar system are all we've known about for a very long time, up until, well, about the mid-1990s. So in particular in 1995 was the first detection of any kind of planet going around another star. Does anyone know the name of this star? It was not the star, a different star to the Sun is what we're talking about. So another star in the galaxy, so another sun. It's the first time we found a planet going around another sun. 51 Pegasi. Congratulations. So the way it was detected was a little bit strange, and we certainly weren't expecting to do that at the time. So if you look at a planet going around its sun, now the planet itself is very faint, so I'll attempt to do this demonstration. Sorry if I get it wrong. Now, I'm a lot heavier than this basketball. Yep. So the key thing is whether I'm moving or not. So am I moving at the moment? No. But you could tell if I was moving. Well, so for a start I might be spinning, but in particular whether I'm moving towards or away from you. So when I'm spinning I'm not particularly moving towards or away from you like that. But if I have a planet, if I'm a star, I'm some kind of star, maybe not that kind of star. If I have a planet going around me, then the key is the planet is not just going around me. I apologise for anyone I damage in this process. Now, so there's a word there. Is something happened to me, which is there's a little wobble. And the wobble got a bit bigger, actually, as the time went on. So the key thing about 51 Peg is we detected a little wobble. Now, the thing about planets going around stars is it's not true that planets go around stars. So planets don't just go around the sun. Anyone actually studying here? Go on. Oh, hands up means I have to tell a joke. What do aliens like to read? Comic books. So it's not just true that planets go around the sun, but the sun also goes around the planets. Well, more correctly, they both go around the centre of mass. Now, I'm much heavier than the planet, so I don't really move very much, but I do move a little bit for the fact that a planet's going around me. And that little wobble of me sort of doing this as the planet goes around is what you can detect. Now, so this is the first planet we detected like that, and nobody was looking for planets like this. So you see this wobble up and down in basically the speed of the star as it's coming towards it. So it's just the Doppler shift in the light from the star. And it's caused exactly by that kind of wobble that I just tried to describe. Now, the really weird thing is the period of that wobble in 51 Pegasi b, and it's up there on the plot. You read what it is? 4 days. Now, how long does it take the Earth to go around the sun? Approximately 1 year. Thereabouts. By definition, 1 year. So 365 days. But a planet, so this planet was a planet that has more than the mass of Jupiter and orbits its star every 4 days. So the reason why we weren't looking for planets is we weren't expecting anything like this. And so a bunch of the planets that were found first up in the late 1990s were found by this method, And this sort of, it was quite interesting because this sort of field was kind of not very interesting astronomy at the time. There's people looking for binary stars. You know, we know a lot of, half the stars in the galaxy are binary. So it was just not a very interesting thing to do, but, detection of a planet just lit up the whole area. I mean, this is, so I have a little star there as being the first because there was a couple of detections. First of all, there was a couple of detections in hindsight where people had really detected a planet, but they didn't really think it was, and they hadn't. But in hindsight, when you go back, they really had detected a planet. And there's one set of planets discovered in 1992, which were discovered by people at Swinburne who were involved. Were around nothing like a normal star. Does anyone know what those planets were discovered around? So discovered around a neutron star or a pulsar. And we've discovered several planets around pulsars since, but they're in a sort of special category, and they're nothing like planets around a star like the Sun. So since then, the race has been on to try and identify anything which looks vaguely normal in terms of planetary systems. Now, there's a couple other methods you can look for planets. Does anyone want to hazard a guess at the next most common one? Ooh, gravitational lensing, now we're getting complicated. I'm not going to talk about that tonight, actually. So gravitational lensing is a particularly clever way, which is that when a planet goes in front of the star, you can see a sort of brief, it's like a lens passing in front of the star, and you can see a brief brightness increase in the star's light. But it tends to, you have to just catch something. It's very hard to do, and you can't go back and see it again. So it has some, so definitely that's one method. But it's not the main method that's been used since. Right, so transits. So it's a pretty obvious technique, which is that if I transit in front of the projector, perhaps I can do that. Yes, my party cat can transit in front of the projector. So you can detect the fact that I'm here. Well, perhaps you can see me. But by the fact that I dim some of the light from the projector. So if a planet happens to pass in front of the star, so it eclipses the star. Now this is a transit that many of you may have seen, happened a few years ago. Does anyone know which planet this is? Someone's already said. It is the Sun, well done. And it is Venus. So this is exactly what we're looking for in other planetary systems. There's a very little tiny dip in the light, and we can detect the presence of planets going around other stars by looking for those very tiny dips. And in particular, there's a mission called Kepler, whose job was just to stare at a very starry patch of sky for a very long, well, for now 3 years until it broke. Well, one of the wheels broke, and so it went all wobbly. It's actually carrying on, but it has to, it's a very clever way of carrying on. So it's kind of like on the side and tilting. So they've enabled Kepler to carry on looking at different patches by lining it up in the plane of the Sun, so the Sun kind of keeps it in balance. And every sort of few months they have to turn it the other way so the Sun doesn't shine in the end. But it's limping on and still doing good science. In fact, it's sort of doing more interesting science because it can't point at the same patch all the time anymore. So it has to look at different patches. But for the first 3 years, Kepler was just staring at this one patch of sky and looking for little dips of planets in front of stars. And in that time, discovered, does anyone know how many planet candidates Kepler found in that time? Of order? Well, how many candidates are there? So of order, yeah, 3,000 or 4,000 new planets around other stars. So in terms of the effect on how many planets we knew of around other stars, here's the plot. Up to, so 1995, there's your 51 Pegasi, and essentially all these planets in the blue here are the ones found with that radial velocity technique. So the one looking for the wobble. And the green is planets found with transits. So we found a few, sort of 2004, there's a sort of little green on top of the 1998 there. But Kepler came online and confirmed, 800 planets were confirmed in 2014 alone. And there's another sort of short list of 3,000 or 4,000 waiting to be confirmed with follow-up techniques. And in that, we just got this treasure trove of wonderful whole planetary systems around other stars. And now we're starting to boil down to not just well, we've discovered some crazy planets around other stars, but what kind of planets are common? And so that's part of this story of, how common is life in the universe? Part of that question is, well, how common at least are planets like the Earth? And Kepler has basically answered that. And just discovering some pretty crazy things along the way. So this particular system is known as Kepler-67. You can see the artist's impression, done 30 years ago. It's Tatooine. So it's a planetary system where you've got many planets going around 2 stars. And certainly we didn't expect these kind of things, but we now know of about 7 or 8 multiple planetary systems going around 2 stars, which a lot of them we didn't even expect to be stable. I mean, here you've got 2 planets going around 2 stars within the orbit of Venus in that kind of planetary system. So it's pretty special. Right, remember to put up your hands if you need a joke, kids. Oh, we've got one more. All right. What kind of music do planets sing? Neptunes. All right, so there's one of my favourites, is Kepler-62. Again, it's a sort of whole solar system. Again, just because of the method of detection, you're very sensitive to things that transit multiple times in front of the star. So you tend to find things that are much closer to the star than our own planet star. So by definition, how long would you need to wait to see a transit of the Earth around the Sun? A year. And to really get a detection, you need at least 3 transits. And how long did Kepler run for before it broke? 3 years. So it's just marginal. So the kind of time when Kepler stopped was just the interesting bit, when we're just getting to things that were sort of Earth-sized, a little bit bigger, in sort of Earth-placed orbits. But one of the things, because it really just stared at a sort of continuously stared at a patch of sky, is you can really answer, well, how many stars in general have planets around them? So there's a nice graph. Oh, and there's one more thing as well. So here's a nice sort of visualization of all of the multi-planet systems detected by Kepler. Now, don't ask me why the tune is Ride of the Valkyries. Well, you're either all awake or you're all now hypnotised. So I'm not sure which. But in terms of the question we're trying to address tonight, Kepler answered a very important one. Now, the uninteresting bit about Kepler is they're all miles away, because it stared at a patch. It wanted to get as many stars in the field as possible. So they're all on the sort of far side of the galaxy, where you can never hope to get a proper image or a follow-up. So it was very good at answering this question of, well, how common are planets? But the kind of planets it discovered are hopeless to follow up on. All right, so here's the plot basically answering that question, is how many of those stars have planets? Well, there's the fraction of stars with Earth-like planets, super Earth-like planets, mini Neptune-like planets, large. So if you add all those things together, and we're starting at 17%, 20%, so 17 add 20 add 20, more or less every star that Kepler looked at had planets of some kind, which is pretty significant. So we've gone from not knowing if any other stars like the Sun have planets to knowing that, well, at least 70%, so basically all of them, have planetary systems of some kind. Now, how many of them have Earth-like planets where, well, the definition of Earth-like here is between 0.8 and 1.25 Earth radii with a period of less than 85 days. And that's really just because you couldn't detect many more than that. So you couldn't quite detect Earth because it didn't have enough time. But so 17% of all stars, if you extrapolate, and Kepler stated 100,000 stars, so it's a pretty good number. And this is accounting for the ones that weren't detected because they didn't have enough time or didn't have enough sensitivity. So 17% of how many stars in the galaxy? Anyone want to hazard a guess? Be over 100, yep. Any advance on 100? 100 billion, about 100 billion stars in the Milky Way, which we don't count them all, but we know roughly how much the Milky Way weighs. We know how much the typical star weighs, so we can work out roughly how many stars are on the Milky Way from how much it weighs. And the answer is about 100 billion. So of 100 billion stars, 17% of that is a lot. All right, so that's kind of interesting. If you then, that's of the ones that are Earth-like. So you like to think, well, in that list, then, and a bunch of them are really close to us as well. So they're sort of collecting a list of potentially habitable planets, which are planets a bit like the Earth, not so far, far enough away from the Sun that they can possibly have liquid water. It's pretty interesting. And so in terms of a possibility for life, we've at least got that first part of the question, which is, planets appear to be pretty common in the universe. Right? There's one more method of detecting planets I want to talk about, which to me is the most special and the most obvious. Take a picture. So taking a picture is not as simple as it sounds. Andrew's taking a picture right now. But so what's the problem with taking a picture like that is that the star is so bright it would damage your camera. So the tricky bit about trying to take pictures of other solar systems is you've got to block out the light from the star. That's what causes that great ugly blue purple mess in the middle, is trying to get rid of the starlight. So this is one of the first pictures of another solar system. It's HR8799, creatively named. And B, C, and D. So we always call the star A. So B is like the first planet seen around the star. C is the next planet we find. D is the next one. And this was in 2008. So that's the first picture of actual planets going around a different star to the Sun. And what got even more interesting, so this was in 2008, was that in 2011 the technique for subtracting the star got a bit better, and they took another picture. Spot the difference. There's 4. Right, and so these are pretty far away from the star. So 20 AUs, 20 astronomical units, which is the distance between the Earth and the Sun. So Pluto in our own solar system is about 40 AU. So these are a lot further out than, well, E would be 20 AU roughly from the star, if you look at that plot. So these things are pretty far away, and the sorts of planets you can see like this are not going to be things like the Earth. The Earth does not radiate very strongly. So you tend to see things that are sort of several times Jupiter in mass. So these are quite massive planets, but it's the kind of things we can really get pictures of. And so I guess the hope is one day you'll be able to do this for even smaller planets with an even more sensitive telescope and peer right in and see the picture of the beachfront property and the kind of holiday destinations and their radio telescopes pointing at us. So if we really want to get direct signs of alien life, then perhaps direct imaging is the way to go. And that's probably the most spectacular one, but there's a number of other direct detections of planets going to other stars. Here's another one. So part of the thing you have to worry about is these artifacts from blocking out the central star cause things. So there's a question mark around the C there because you're not quite sure if it's really a planet or if it's just a blob from, masking out the star. So the question that comes in the final part of the talk is how these planets get there. And in particular, this is, I guess, my baby because it's the field, it's the area I work in. Well, it wasn't really, but it's suddenly become interesting. So I work on how stars are born, but what we've learned in the last couple of years is that you can't really separate these two processes. So what's this? Let's put us in some kind of context. What is this picture of? The Milky Way. Well, it looks a bit like the Milky Way, and the reason I put it there is because it looks like the Milky Way. Do you know what it's a picture of? I'm looking for a G word. It starts with G and ends in galaxy. What kind of galaxy? All right, so the interesting thing about spiral galaxies, and if you were here for my previous talk, what's special about spiral galaxies? Anyone was here for my previous talk? The MoCA Centre. You can view it on YouTube. So we went through this argument in a fair bit of detail. Well, there's two interesting things about spiral galaxies. One is that we live in one. So the Milky Way is a galaxy very much like this one. And the other thing that's interesting about spiral galaxies is what they do every time they go round. So in particular, the argument I sort of went through in the last talk I gave was how long it takes the sun to go around the galaxy. Does anyone know the answer? So that's how long it takes the Earth to go around the sun. But the sun is just a star about there in the Milky Way. So how long does it take the sun to orbit around the Milky Way? Yeah, we're in the 250, 190, we're in the hundreds of millions of years. So it takes about 230 million years for the sun to go around the galaxy. But you see a lot of these very hot, young, well I say young, the very hot blue stars are called O stars. And what's interesting about them is they burn through their fuel very fast, being 30 million years or so. But 30 million years is quite a short time in the context of a galaxy like that. Because how long does it take for the galaxy like that to go round? About 200 million years. So this means that every time what you're seeing as a spiral galaxy is basically a giant star factory. So these blue stars are born right there in these dark, dusty lanes of the spiral galaxy. And every time the galaxy goes round, it converts gas and makes stars. Now, stars like the sun live for a long time, like 10 billion years. And so they can stick around a long time. But what you see that's so spectacular about spirals is these really hot blue ones. And we know that they must have come from not very far away because they're dead by the time they get out of the spiral arm. So you see there's no blue stars down here, for example. So they're really born here and they're dead before they leave the spiral arms, pretty much. Okay, so in terms of studying, well, the processes that go on in the Milky Way, what we do is peer up, well, because we live in a galaxy like this, we don't just have to study distant galaxies. We can look inside at how stars are born in our own galaxy. So what do you think that might look like from the inside? Well, what do you think it might look like from the outside, first of all? So our best guess of what the Milky Way actually looks like is hard to do because we don't see it from the outside. So that's the picture I just showed of M83. That's the sort of best artist's impression of, well, it's a sort of scientifically inspired artist's impression of what we think the Milky Way looks like if we could step outside of it, which we can't. That's what we actually see, which is the plot of, stuff orbiting in the Milky Way and trying to reconstruct back to what it actually looks like. There's a paper we published last year on this, which is our attempt to reconstruct that thing on the right based on a simulation of stuff orbiting in the Milky Way. And you can see it's not so far away from the pictures up the top there. So we do live in a galaxy that looks pretty much like that. And we can peer into the inside at the places where those stars that don't live for very long are being born. So from the inside, what do you see when you look up at the night sky and you see the band of the Milky Way? We see dust lanes. So in particular, for a galaxy full of stars, it's very dark and dusty. And some of these ones that are sort of sticking up out of the plane of the galaxy, so if you look up here, well, there's one called the Pipe Nebula, which looks like a pipe. There's another one just up there. You can see these sort of two dark, dusty lanes. But because they stick up out of the plane of the galaxy because they're really close to us, so the stuff that's far away just looks, or is in the plane of the Milky Way. But the stuff that's sort of sticking out of the plane are the really nearby dusty clouds where stars and planets are being born. So if we want to know something about the formation of planets, that's where we want to look. So if you take this one in particular, that's called Ophiuchus. We can map it, we can plot all the we can map all of the newborn stars. And I'll tell you what I mean by knowing that they're newborn in a minute. That's what it actually looks like on the sky. It's forming a whole cluster of young stars. Now, there's another of our favourites, which is also, doesn't look particularly spectacular on the sky. It's just a sort of dark, dusty blob. It's full of, forming a whole cluster of young stars. But the special thing about these couple of clouds in particular is they're really nearby. Really nearby, 140 parsecs away. How far is a parsec? About 3 light years. But what's significant about, well, if you're trying to work your way around the galaxy, we're not going to use kilometres. So it's a long way to walk. But if you think the nearest star, like Alpha Centauri, is about a parsec away, that's a good way to think about it. Because then the centre of the galaxy is about 8,000 parsecs away. So that's sort of, within the galaxy you're talking about kiloparsecs. So instead of kilometres, we'll use kiloparsecs. But so something that's 140 parsecs away is something that's really close to us in the Milky Way. Nearest galaxy is about a megaparsec away. So that's the sort of scale between galaxies, if you like. And it makes it seem not so scary. So you don't have to think about how many kilometres it is to walk. You can just think about, parsecs, 140 parsecs, it's nearby. But just to put that in context, getting to Alpha Centauri, our nearest star, and back will take about 10,000 years with a good rocket. So we're not going anywhere near. The best we can do is take pictures. Now, the significant thing about star-forming clouds is that, well, we can see the process of making stars in them. So here's another famous one, which is the Orion Nebula, imaged with the Hubble Space Telescope. And in particular, you can see these newborn stars, and they're newborn because they're still embedded in the gas and the dust from which they're born. But I want you to notice what's around them. So there's all this sort of fluffy gas and stuff, but around the newborn star in particular, so there's a disk of gas and dust. Now, so it's like looking at the cradle, if you like. You're looking at all the babies in the cradle, and you can tell that they're newborn because they're still growing in mass and all the rest of it. But that's interesting, and that's why I've sort of got interested in this a little bit, is because every time we see newborn stars, we see these disks of gas and dust around them. And, well, that's something we've known about for a number of years, is produced when we try and make stars in the computer, which is what I do. And here's a colleague of mine, Matthew Bate, in England, who's a New Zealander, so there's Gandalf. But we try and make these computer models of stars being born from the little clouds in the galaxy that we see, and this is a very poor representation of the real thing, but it at least allows us to do some kind of controlled experiment on how we think the gas in the galaxy converts itself into stars. So essentially you just take the rules of gas dynamics and gravity, and you let them do their thing in the computer, and you watch gravity pull the gas together to make newborn stars. But in particular, there's something significant, which I'm going to try this again, that if you take, all right, let's see if we can do this. If you take something big that's spinning around, does this work? You make it, yeah, that worked, and you make it small, what happens? Right, it spins faster. So when you try and pile material onto newborn stars, there's a little example that just flew off in the corner there. I'm now dizzy again. But you can see something that just flew off to the top left there in the movie was a disk of gas around a newborn star. Now, what's interesting about that in the context of looking for life is what do we think happens in those kind of disks? A solar system forms. Very good. Do I have to tell a joke now as well? What did the alien say to the gardener? It said, "Take me to your weeder." Sorry, that's bad. So these disks are the places where we think that planets are made. So sometimes in astronomy, astronomy is a very, my shirt's coming untucked, I'm getting less formal as we go along. Sometimes in astronomy, it's a picture that really changes the way we think about things. So the thing with the Hubble Space Telescope, which was really special, is for the first time we got pictures of the disks around newborn stars. Now, what we didn't get, though, is any kind of picture of what's inside. So of what's inside, what we think might be going on is the process of making newborn planetary systems. And if we think about what we've learned from Kepler in the last few years, how many newborn stars should also be making planets? Or as a percentage? Any kind of planets? Well, all. So there's a bunch of mysteries. So disks are pretty special, and again, some of the classic Hubble images were pictures of, so this is a picture of a disk side on with this jet of gas coming out of it. And you see jets of gas just like when babies burp. It's because you're trying to feed the star too fast with material and it sort of burps in the vertical direction. So, I mean, that was sort of in the early 1990s. Why do we get disks at all? Well, I sort of explained. Not just gravity. Why does stuff start orbiting instead of... Right, so spin, there's a technical word for spin. Angular momentum. So it's very hard to get rid of angular momentum. It's something that's conserved in the universe. So if you take something that's spinning and you make it smaller, it's going to spin faster. Because you have to get rid of the angular momentum somehow. So for example, you might think it's a great plan to dispose of nuclear waste onto the sun. So if we took a little pile of nuclear waste and tried to throw it towards the sun, what would happen? Like that. Is this a good idea or not? You can pass. Why not? Why does it come back to us? Because it's in orbit. So it's still got the orbital velocity of the Earth. So when you throw it towards the sun, it's just going to ping right back out again. And you'll meet your friendly nuclear waste about 6 months later. So nature's solution to this problem is to form a disk. And so that's what we see around all these newborn stars, is to get rid of that angular momentum. You have to transfer it slowly out of the disk to a small amount of material that gets carried away. And so these things are pretty common around newborn stars. And we've seen that they are common for a long time. But there's a very special telescope that has come online the last year or two. I've already written the name. I was going to ask you what the name is. Does anyone know the name of this very special new telescope? ALMA. Does anyone want to guess what wavelength ALMA observes at? So in the millimetre and submillimetre, does anyone want to guess where ALMA is? The Atacama Plateau in Chile, which is one of the highest, driest places on Earth. It was a very dangerous place it is a very dangerous place to work because it's 5,000 metres in altitude, but it's a wonderful place to put a telescope. And in particular, a submillimetre telescope, because you get rid of most of the atmosphere. And, well, it's in the submillimetre means it's almost like a radio telescope, not quite. So it's dishes instead of sort of mirrors. But what's special about ALMA is it has amazing resolution. So unlike with Hubble, where we really can't see inside what's inside those disks, with ALMA for the very first time, we can finally see what's inside. So this picture I showed at the start of the movie is one of the first images taken with ALMA. And what it's pointing at is one of those just nearby star-forming clouds called TAURUS, which is how far away? 140 parsecs. So you can see it's sticking out of the plane of the galaxy. It just looks like a sort of dusty blob in the sky, and they just pointed at the brightest young star in Taurus. Now this is a Hubble image coming up. So the Hubble image, you can see there's a jet coming out of this young star. It's still in the process of formation. It's got gas landing on it. It's in a real mess. Now ALMA took a snapshot, which is coming right now, of what's inside. And what's inside is the structure of that disk. So this is the first time we've ever been able to see in a disk of gas and dust around a young star. And what does it look like? Well, it's got rings. Now, where do rings come from? How do you get rings in a disk? It's like bits are missing from it.
Things clumping together and forming lumps.
Right, so how does things coming together and forming lumps help you get rings?
They sweep up the dust as they go around.
So they sweep up things as they go around and sort of carve, so just like a record player, if you put the needle in the groove and you go down a bit hard, you can scrape a hole, so now you've got a horrible sound in your head, but you can just imagine that instead of actually doing it. But we don't know an awful lot about planet formation, but this is one of the things we've studied for years. It's on the front cover of the textbook. It's a pretty easy experiment to do on the computer as well. You set up a disk of gas going round, and you put a planet in it, and it carves out a nice gap in the disk. So we don't quite know how the planet got there, but we know that if you got planets in a disk, then they should be good at clearing out the material around them. So, well, one of the definitions of whether you're a true planet or not is whether you can clear the material in your orbit. But that's a little bit like what that image looks like, but not quite. And the not quite is because, well, just to show you how much better that is than what we had previously, that is the previous best image of the same disk on the right there at the same wavelength. So you've gone from something which is just a blob to actually seeing what's inside is pretty special. That's why we spend a lot of money on telescopes. But given what we knew about the system before, that was the actual prediction for what the thing should look like, which is hilariously wrong. But in particular, the kind of object that this is, it's a very newborn star. It's got lots of gas. You see that in that Hubble picture, it's got this jet of gas coming out. It's got stuff landing on it from all over the place. It should be a pretty sort of violent, heavy disk, and heavy disks tend to form spirals. And one thing you definitely did not see in that image is any kind of spirals. And so that sort of threw everyone into a bit of a tizzy about what this sort of thing really is. And the same with this kind of process. If it really is planets making these gaps in the disk, then you'd expect to see spirals. That's a simulation that I ran with some planets in the disk of gas, and you can see pretty prominent spirals coming from the planet that you really don't see in that image. So never let a good image get in the way of your bad theory. So people just started wildly speculating this is not planets at all, it's not that special after all, the rings are caused by something else, they're evaporation fronts or something, or their magnetic instabilities, or their dust holes or something like that, but not planets. So we got angry. And the sort of weird thing is that we do know of things that carve quite ring-like gaps in disks. I was going to ask you the question of where that is. I can still ask you that question. Saturn. So what's different about... So Saturn, a lot of the rings in the holes in Saturn's rings are caused by moonlets, or little moons, that carve out these gaps. Now why do they not sort of have the sort of spirals that we see in the gas disks? What's different about Saturn's rings to a disk made of gas? So, they're made of rocks, and there's one other thing as well. So, when you see them side on, compared to that disk that we saw with the jet coming out, what's the difference side on? It's very thin. So when you have a very thin disk, then you don't tend to see this sort of spirally stuff. But that's a bit like what that image of HL Tauri, because in Taurus, looks like. So, well, science is done by Facebook these days. I mean, the teaser about this image is that they didn't even give us any information. It was a press release done in November last year. So they just put that image I showed on the web. No scale, so there's the scale that someone's helpfully drawn on the image. But you can see this speculation starting as well. So Dimitri says, you know, it's just too clear. If there were planets, wouldn't you expect to see some spirals, you know, or something like that? And then you start to get people on about flux rings and, you know, other sort of things we invent to explain things we can't understand. And, you know, some imagination, maybe it does look like planets. And so a collaborator of mine, Giuseppe Lodato, you know, whipped up a kind of image that looked half good, but from a system which is completely wrong. So we took a disk, that's from a simulation of two black holes merging with a disk of gas around it. But the reason it's not bad is we started, in that simulation, we took a very thin disk. So for a disk that should be a bit like what we saw with Hubble side on, so a disk around a young star should look something like that. It should be nice. So what you don't see the disk here, you see the reflected light from the disk. But you can sort of tell that it's, you know, it's got this sort of flared shape, and you can see it side on. It's quite a thick looking thing. It's not really a thin thing. Well, that's the sort of thing we should be looking at just from the top. So why does it look something that's more like that? I've already given you the clue. I'll give you the clue again. And here's another clue. Pass it around. It's my dust collection. It's my belly button fluff collection. Well, it's just generic material from under the bed. So it's been in my office for a couple of years now. But I may break it open a bit later. We'll see if there's any alien life in there. So that's the clue. It should spark a word in your head. Dust. And the other clue is there. What size dust? Right, so what are you seeing with ALMA? You're not seeing the gas. What are you seeing in that picture is not the gas. And so what sort of threw everyone off the track a little bit is that this image that we see is not the gas disk. So that's a simulation of the gas in the disk. So what we really need is a simulation of dust. Now, it so happens that we've been working on trying to simulate dust in disks for the last, 7 years. So we had a kind of code ready to go that seemed to be a good application for this. Now, what does dust do in disks? And you know from looking at that jar, now this room it clumps. There's something else that dust does. Yeah, someone said? Settles. So the dust settles under your bed. Why? So gravity. Well, why doesn't the air settle under your bed? Air feels gravity. Why doesn't it all go under the bed? Air is light, but dust is light as well. It's a gas, thermal activity, otherwise known as, makes your bike pump hard to push. Pressure. So the air in the room has pressure, which holds it up. So a gas has pressure to hold it up in the Z direction, or in the vertical direction, and dust doesn't really feel the pressure. Well, it feels a drag, like when you go skydiving, you feel a sort of drag through the atmosphere. And so it's coupled to the gas, but in general it just feels gravity, but doesn't have anything to hold it back up the other way, unless it's really stuck to the gas, like the small grains can be. So this is a side-on view of our simulation. There's the gas and there's the dust. What does the dust do? Settles into a nice, thin disk. All right, so then when we make a face-on movie, you can see the planet's making nice spirals in the gas there. So we've just plonked 3 planets with masses tuned to give us the right kind of holes. And you can see you make nice sort of circular, much more circular rings in the disk of dust. Now, we took our simulation and ran it through the telescope simulator that makes it look like what Alma would have seen if you put it at the right distance and all the rest of it. What do you reckon? Now, what's interesting about this, and again in terms of the search for life, well, so can we explain what's going on in this disk with planets? Very definitely. So, I mean, the confusion about the spirals just seemed to be that we missed the fact that we're actually observing dust and not gas. But what's frightening is that this is going to throw all of our ideas about how planets got there out the window. Because, well, what kind of place was this seen in? What sort of, so in a nebula like TAURUS, which is sort of basically a brand new, still got a jet coming out of it, it's got gas landing on it, that star is less than 1 million years old, which is very young. So if you're less than 1 million years old, hands up, you're officially very young. In the context of the Milky Way, you're young. Just tell that to your grandkids. So, I mean, a star less than 1 million years old that has rings all over the place, and what kind of planets do we need to make those rings is a question we can now answer. Have a guess. Not just rocky, big. So things like Saturn mass. Now, to get Saturn mass planets that early in the process is, a lot of erring. And it's interesting because here's the recipe for making planets, or at least the sort of standard view, and there's certainly other views. But now kind of the game is open in a way, because our standard picture is, this is how you make planets. Can I borrow some dust? Anyone got the dust? Let's make some planets. Dust collection, anyone? Let's pass the dust collection along. Should have done this earlier, thank you. So we need to, now if anyone dies from this, so we'll take some dust. Ooh, very good. Leave some behind in the nebula. And so, the idea is that the dust is quite good at sticking together and makes, and makes bigger dust. But, well, you're meant to do this in a disk. So we need gas, dust, and a disk. So here's my equivalent of a disk. The idea is you take the dust and you have it in the disk. Not all of it sticks. But eventually you clump the dust together to make planetesimals. That's my planetesimals. And eventually you clump the planetesimals together to make... So the bake time is about 10 or 20 million years. You smush the dust together to make planetesimals. Another few million years, you stick the planetesimals together to make sort of rocky cores, a bit like Mars. And then the sort of crowning glory of planet formation is meant to be that you get these gas giants right at the end. So you then add gas. That's not going to end well. if I add gas. So we'll do this in real time. So I'll add it slowly over the course of the next 5 million years. But the really interesting thing then is that the universe appears to be making planets much quicker than we ever thought possible. So this whole process that we've sort of studied, but don't really understand in depth, was thought to take more like 10 or 20 million years. But now we're sort of seeing signatures of planets like Saturn mass within the first million years, which is a really short timescale. And so, well, this is not the only kind of observation that we're getting of disks. There's other instruments coming online. Also, this is a paper published in August of an image on the right of a similar disk around a young star called MW, a slightly older star, like 4 million years, MWC 758. And on the left is someone else, probably our competitors now, done a simulation of this disk and tried to reproduce this big whopping spiral that you do see in this case. Now this is an image more like the gas, so you see this big whopping spiral. What have they put in the disk to make that big whopping spiral? Have a guess. It's green. A big whopping planet. So they put in a 5 Jupiter mass planet to make that spiral. And you can see it does a pretty good job. So the picture on the left is the simulation, and the one on the right is the image. So it's sort of telling the observers to go look. And if you look there carefully, you should see a 5 times the mass of Jupiter planet. So the new thing for me is that now we're seeing inside of these disks where planets are being made. And as from the earlier part of my talk, it should be really no surprise that what are we seeing? What are we seeing? We're seeing the signs, we seem to be seeing the signs of planet formation everywhere. So there's a 5 Jupiter mass planet there. And there's one final thing that I'll mention, which is that we've known for a long time that the way that disks appear to go away and here's my favourite Kylie CD. So often we don't resolve the entire disk, but you can see the spectrum of the disk, which is much like when I shine at you, you see a little rainbow. So that plot up on the left there is a bit like a rainbow from a disk around, various disks around a young star. And as they get older, there's a dip that happens in the middle of the spectrum there. That's the green one compared to the blue one. And one bump there is from the star, and the other bump is from the disk. And the interpretation of that bump is that all the disks start getting a hole in the middle. And eventually the whole disk goes away. So these are called transition disks. And we're getting some first images of these, that they really do have holes in the middle. But what might be causing these holes that makes all of the disks go away, so this is a very common thing, that all disks appear to disappear like this, appear to disappear. And the intriguing possibility at the moment is maybe all the disks go away because it all turns into planets. So the other mechanism we have is that the dust gets evaporated by the star. But at the moment, these two are sort of, competing ideas. But the photoevaporation doesn't work, has got a lot of problems. And the planet explanation is pretty interesting. And if we put that in context with what we know about planets everywhere else, it's consistent with what we know, which is basically all stars, all newborn stars are making planets. All stars in the Milky Way have planetary systems around them. Have we found any aliens? No, but watch this space. No pun intended. So I hope I've tried to bring together something of what we are discovering, and it's a pretty hot field at the moment in terms of, these are our first images of these things, but as you saw from the picture, there's sort of thousands of disks in TAURUS that we could possibly take pictures of. So we're expecting a lot more, but the thing we've seemed to have come to a pretty solid understanding of is that planets are very common in the universe. And hopefully within the next 10 years, we'll probably find out that Earth-like planets are common. But the next stage is really to then find out more about them, what's on them, what the atmosphere is made of. And we're already starting to do that. I haven't talked about that very much. But it's possible that in our lifetime we'll have an answer to this question that we've been asking for thousands of years about whether we're alone in the universe. So thanks for your time.
Well, thank you very much for an interesting talk, and now we have some time for some questions.
We tend to concentrate on Earth-sized planets rather in our own image, as it were. And we know from our own planet that life exists in a variety of different and sometimes hostile environments.
Yep.
So why are we just looking for Earth-like planets when we could have, most planets could have life of some form of which we are unaware?
Well, I'd say I think there's a deep thing there about one of the reasons we didn't look for planets around other stars when we could have detected them at least 10 years earlier is because we were thinking that everything was like the solar system, and it's not. But I think that picture's... So, I think part of the answer to the question is now we're basically detecting what we can. That said, the search is still concentrated around stars that are kind of like the Sun. So, like, the radial velocity searches are all targeted to Sun-like stars. So there is a certain bias there towards trying to find things like our own. But I think we've got a pretty good picture now of how common our solar system, not quite yet because we can't quite detect our own solar system, but if we've learned anything from astronomy, we know that the Sun is kind of an average-sized star, and we'll probably find that the solar system is just, there's quite a few. It's a run-of-the-mill solar system in terms of the galaxy as well. So I don't think it's an unfair bias either, perhaps. Given that I would say our solar system-like things are probably likely to be common. So
we always argue about the Goldilocks zone.
Sure. Yeah.
That presupposes carbon life forms, perhaps.
Well,
why not other places?
so in a way, the best way to answer that question is the first part of my talk, which is let's go there. Let's go to Europa, go to Titan, which are places that are very much not like the Earth, but have these interesting environments that could support something, but nothing like life on Earth. The place to answer that was with missions in our own solar system, I think.
Can we detect what planets are made of?
Yes. So one of the wonderful things about the technique about planets going in front of the sun, of their stars, so that transit method, whether it's the planet goes in front of the star, is if the planet has an atmosphere, a little bit of the starlight comes through the atmosphere of the planet, and you can see what that's made of. So you can see a spectrum of the atmosphere, and you can see what the atmosphere is made of. It's very hard to do, so we only have a few of these sort of measurements, but we can see that some of the atmospheres of these planets have water in them, for example, which is quite interesting. So yeah, you can see what they're... See, there's another answer to that as well, which is that you can measure not just how big a planet is, but how heavy it is. So that means you can see how dense a planet is. So you can tell if a planet is rocky or gassy by how dense it is. So there's two ways. So yes.
Mike's coming down.
Someone mentioned the habitable zone. I wonder, in looking at the planets which are habitable, would you be looking at the ratio of how much light the planet reflects from the star versus its eccentricity of the orbit?
Yeah, I mean, so this is a field fraught with difficulty. I mean, the conversation's kind of moved further than that. So that sort of simple picture has well and truly gone out the window now. So people are doing pretty serious. So actually, some colleagues of mine in Exeter are working with the Weather Bureau to use the weather forecasting codes to forecast, weather on other planets. So I mean, but one of the interesting things you can answer with that kind of question is, so there's various things like runaway. Venus is in sort of in the habitable zone, but it's had a runaway greenhouse effect that hopefully we won't have. That that makes it completely uninhabitable even if it's in the right place. So I know there's at least 5 different definitions of habitable in what sense, and so it's a very subtle question, and it involves a lot of sort of climate science and all sorts of things about what actually happens. The Earth, or even different places on Earth, are very different habitability. It's a very complicated question, but the field's got more. The field has got more sophisticated as there's more things to think about. So, yeah.
Yeah, just a quickie. Thanks, Daniel. That's great talk. Very interesting always. You mentioned about no aliens yet. Watch this space, and we may well find out about them. In which way do you think we might find out about them?
It's a good question.
Is there some preferred system?
I would have said our best chance is finding. I mean, the things that we have hints of already is what's in the atmosphere. So I would say our best chance is to get. Well, either we get some image and we see lakes, and that's on a sort of 20-30 year time scale before we can get telescopes like that. But in terms of getting like biomarkers in an atmosphere, so for example, I mean, humans at the moment are doing a good job of affecting the atmosphere. So there's certain things that life does, like produces carbon dioxide from oxygen. So the Earth was very much. Well, the atmosphere has been changed by living things, quite significantly. So that if I was to put my money somewhere, it would be on
Fair enough. Thank you.
finding chemicals in the atmosphere that have to be sort of signatures of life. Oh, I can tell you all the time. I've told yours already. What did the alien say to the cat? Take me to your litter. Well, sorry? Well, here's a better one. What's an alien's favourite place on the computer?
Space bar.
Oh, we got it. Did you catch it? The space bar. Do you want, I've got a couple more. Oh, why did the Martian throw beef on the asteroid? He wanted a little meteor. The internet's a wonderful place.
Okay.
Of the planets you're observing now, are we able to detect magnetic fields in planets that far away?
Ooh, that's a really good question. It's also a topic I work on, so I should know something about. I don't know if anybody has ever tried. That's a very good question. Because, I mean, certainly for the Earth, that it's a very important. I mean, certainly on planets in the solar system, we know quite a lot about the magnetic fields from actual measurements. Yeah. It's a very good question whether you can. I don't know the answer. And I don't know anyone that... I'm not aware of anybody who's trying to answer the question. But it's an interesting one, yeah. I'll think about it. Thanks.
Just a little one, Daniel, a bit tongue-in-cheek. If we estimate that there may be life on other planets with the pollution in the atmosphere and stuff like that, does it follow that if the planet's got a lot of methane gas, there's be a lot of cows there?
Yeah, I mean, that's a good point. We can be easily misled. And I think that's even true if you take the example of seeing, seeing what we think is planet formation in a disk. There can be a lot of argument, even about something which is, which is visual, that you can think would be interpreted relatively easily. There's been a huge debate. There's at least 15 papers suggesting different explanations that aren't planets for that disk. So I'm sure if you came up with, anything in an atmosphere, there would be 100 non-life-giving explanations for why it's there.
Right. Thank you.
Yeah.
Okay.
That's a good point.
Just a quick
Final question.
Just recently, we've seen that they've discovered ripples in disks around the stars, moving very, very fast, and they don't know why.
Yep.
I'll throw your hat in the ring for that one.
Yeah, this is wonderful stuff. So one of the answers is companions. So other bodies in the disk, if they're not aligned with the disk plane, so some of these holes in the middle of disks, one of the ALMA images, which is not quite an image where you have to look at the artist's impression as well, is there's sort of, some of these disk holes in the middle where we think they might be due to planets, they're seeing sort of quite complicated streamers and, what looks like sort of gas that's, freely falling in from the edges of the disk. Which is interesting because, again, in some modelling we did for black holes, we find that, you can actually do interesting things with disks whenever you have some sort of torque which is not aligned with the plane. So if you've got a companion that's out of the plane, or you've got, a companion over there that's not aligned with the disk plane, you can rip things off the disk and make it do interesting things. So, we were cited in that paper for from one of our black hole simulation papers. But it's a super interesting. We need a bit more resolution to really see what's going on. But companions is what we're hoping is the answer to that. But misaligned companions in particular. Well, what we're expecting in the next, I already know there's sort of things that are top secret, but everyone's excited about. But everything that's coming along in the next probably 12 months is lots more images of disks. And the sort of rumours are lots of warps and spirals, and this is the first time we've been able to see in them at all. But all this kind of complicated stuff going on, which is very interesting. It's stuff we've been able to model for a long time. So it's stuff we actually have quite a bit of theory about, but we've never been able to really see. So it's pretty good.
Okay, well, thank you very much for a very interesting talk. And as a token of our appreciation, a nice bottle of wine.
Thanks.
So let's thank Daniel again.
It's one parting gift. What do you get if you cross a kangaroo with an alien? A marsupial.